Hello everybody. In today's video, we're going to be learning about, or rather we're going to be looking at inferences for linear regression. So the big guiding question behind all this is, can the circumference of our head predict our height? So let's have a look at how we do this. So the table on the right there represents 10 children who were randomly selected, and their head circumference in inches and their heights in inches are recorded. So the data, like I said, is shown right there. So what I would like you to do is do three things. I would like you to describe the relationship between the circumference of the head and the height. And then I would like you to determine the least squares regression line for that data. And finally, I want you to interpret the slope of the equation in context. So if you want to practice at this, why don't you pause this video and just basically take 3 to 4, 5 minutes, see if you can figure out those answers, and then press start again, and we'll see how we did. All right, so let's go through this question. So the first thing I want to do is I want to have my graphing calculator right here, and I want to input all that data into L1 and L2. The reason I'm doing this is I want to be able to create a scatter plot. The whole idea behind this is, do we have a legit linear correlation so that I can really use a linear model to describe the data? So the way we do that, we go to second y equals. We're going to turn plot number one on, and we're going to go ahead, set up scatter plot, and we're comparing L1 and L2. So then we're going to do zoom, and then number 9, okay? And that's always going to give us our scatter plot, and it's going to basically adjust the screen so we can see it perfectly. So when you're asked to describe the relationship, remember you always want to talk about the strength, the direction, and the type of correlation. So in this case, there's a strong positive linear correlation. All right, let's go ahead and do the second question, which was to come up with the least squares regression line. So the way we want to do that is we want to go to Stat, go to Calc. Now you could use number 4, but I find it a little easier to do number 8, the linreg a plus bx. Now I'm using the older calculator here. That way, it doesn't matter what kind of calculator you have, you should be able to follow these steps. So we're going to do second L1, comma, second L2. So what we have now is our value for A and our value for B. So remember, A is the y-intercept, and B is going to be the slope. So to put it into context, the least squares regression line is going to be the predicted height, don't forget that little arrow on the top, equals negative 50.37 plus 4.43 multiplied by the head circumference. All right, and then finally, to interpret the slope of that equation in context, for every 1 inch increase in head circumference, there is a predicted, make sure you don't forget that word, a predicted 4.43 inch increase in height. All right, so let's continue on. So in today's lesson, we're going to be doing two things. So we have these two guiding questions. So the first guiding question is, what is the value of beta or beta, depending on where you come from, which is the slope of the true regression line? So what I mean by that is I could take another sample of 10 children and get a different value for B, the slope. I could take another set of 10 children and get yet another value of the slope. So the thing we're going to try and answer is what is the true slope of that regression line, or what is the slope of that true regression line? The second guiding question we're going to answer is there a significant linear relationship between the two variables? So we can see on the scatter plot that indeed, there does appear to be one, but we want to see if there's a significant one. So we're going to use procedures similar to other topics. Okay, so when we're talking about trying to find the true value of the slope, we're really talking about confidence intervals. Now, the one point I do want to make here is you can get your information in two ways. Maybe you're doing an experiment where you actually have set conditions in a set environment and you're trying to see if one reaction impacts something else. Alternatively, you could just be getting data from the population, and then you're coming up with the population regression line. So if it's an experiment, we're going to be talking about the true regression line. Otherwise, if we're using a population, we're going to be talking about the population regression line. Now, when we come to answer the guiding question number 2, that's going to be a test of significance, and we're going to use our calculator to do a lin-reg t-test, or a linear regression t-test. So before we do that, let's go up and check some things. So whenever we're trying to do a confidence interval, or if we're ever trying to do a significance test, we always have to check conditions. Now, for linear regression, it's a little different. There are some similarities, but there are also some differences as well. So the first thing you want to do is you want to start by making a histogram, or a normal probability plot of the residuals, and also a residual plot. And we'll see how to do that in a few minutes. So the first thing we need to look for is does the data appear linear? So we want to examine the scatter plot to check the overall pattern is roughly linear. So there we have our scatter plot. Okay. Now the next thing we want to do is we want to look for any curve patterns in the residual plot. So let me show you how to do that residual plot. So the first thing we want to do is we want to calculate the residual. So what I'm going to do is I'm going to go to Stat, and then I'm going to go to Edit. And I'm going to go to L3, and I'm going to highlight L3. And I'm going to ask the calculator to calculate the residuals for each of those values. Now remember, the residuals is always the observed value minus what I would expect to get. So here's how we can do that. I can go to Second List, which is the Stat button, and I can go down to number 7, which is residuals. Now, only do this if you've done the least squares regression equation, which I just did. If you haven't done that, make sure you do it so that when we calculate the residuals here, it's calculating the residuals for this data. So if I go ahead and press enter, it gives me all the residuals for this set of data for these 10 children. So now let's go ahead and do a residual plot. So a residual plot is just comparing the head circumference, which is in L1, with the residual. So the residual is always on the y-axis. So we go to second y equals, turn the plot on. We're still going to do a scatter plot, but now it's going to be L1 versus L3. So again, our x values compared to our residual values, or our head circumference compared to our residual values. So now we're going to do zoom 9, and there's our residual plot. So if you look at it, there's no discernible pattern here. Okay, so we have kind of random scatter. So therefore, that's a good indication that we're going to have, like I said, we're going to have a linear pattern right here. Okay. Now, another thing you could do is do what we call a normal probability plot. The way to, and that's of the residuals. The way to do that, do second y equals, and then go to the first one again. And the normal probability plot is this one here right at the end. And we're going to do it of our residuals, which remember was stored in L3. And then we'll do zoom 9. And there we go. So basically, if your normal probability plot looks roughly linear, then you have a good indication that we are using linear data. So that's the linear one. We also want to see if we have independence. So look how the data were produced. Okay, well, we took random samples. All right, we basically picked a random of 10 kids. So therefore, we've got the random sampling in place. However, because we want to check for independence, we want to see if the 10% condition holds. So can we assume there's going to be more than 100 children in the population? Yes, we can. The next thing we want to do is check for normality. Now, we already did the normal probability plot of the residuals, and there was no obvious skewness. There was no obvious outliers. So in fact, we still have it up right here. So therefore, it's pretty safe to assume that we can assume it's roughly a normal, the distribution of residuals would be roughly normal. Now, this one right here is a little odd. So we're looking for the equal standard deviations. So basically what that means is we want to be looking at the residual plot, and we want to make sure that the vertical spread of the residuals is roughly the same. Like we don't have any like massive patterns going on or massive deviations. So if I go back and do another residual plot, so again, go back to scatter plot and then do L1 against L3. Remember, L1 was my head circumferences, L3 was my residuals, and then do zoom 9. There's no, if you look at the vertical distances here, there are some similarities, but there's no like major differences. So therefore, we can kind of assume here that we have equal standard deviations. And then the last one you want to look at is random. Was the data obtained in a random way, or did I allocate subjects to groups for an experiment in a random fashion? In this case, we did pick kids randomly, so therefore we've met all these conditions. Now, to help you, there is an acronym you can use, and that's LINER. Okay, so if you remember that, you can check all your 5 conditions. Now, in the AP stats tests, from what I've seen so far, most of the time they tell you that the conditions are met, but if they're not met, you would need to go through and explain each one using context and using the graphs to back it up. So I did write this out for you so you can see what it would look like. Okay, so that's basically what I just talked about. So linear, the scatter plot appears to be roughly linear, and the residual plot shows random scatter. Independence, we can assume the population of children to be greater than 100. And normal, the normal plot of the residuals shows linearity, and there appears to be no major outliers or skewness of the residuals. Equal standard deviations, the vertical spread of the residuals is roughly the same. And finally, for the random one, the data was obtained from a random sample. So now we're all good to go. Okay, so when we're looking at inference of regression, we're looking at two, really, no, that's not true. We're looking at one parameter. There are two. We could be interested in the true y-intercept, but for the AP stats curriculum, we're not covering that. However, we are interested in the true slope, which is given by the letter beta. So one thing that we will need in order to calculate confidence intervals and to also look at the test procedure is what we call the standard error of the slope. Now, this is the formula for it right here. It is also on your formula sheet. So S right there, that's the standard deviation of the residuals. Sx is the standard deviation of all the x values, which in this case would be our head circumference, and n is going to be the sample size. Now, it's normally given to you, like I was looking at all the free response questions that have been given over the years, and almost all of them give you the information as part of a mini tab display. So this is what it looks like. And you've seen this before when we did chapter 3 on linear regression. So they'll give you this, this chart here. So the constant, so remember, we're looking at head circumference here. So when we talk about the constant of the coefficients, that's going to be the y-intercept. And when we talk about the head circumference coefficient, that's going to be the slope. So we can recognize those values from before. Now, there are some additional ones. S down here, like I just mentioned, is the standard deviation of the residuals. R squared here, which is the coefficient of determination, that's 81.6. So you can use the calculator. You can actually find that out in the calculator. And we've got 3 other ones right here. So this is one of the big ones that I was talking about. So the standard error of the head circumference, or the standard error of the slope, okay, will be 0.739. And then here we have our test statistic, a t-value of 6.007. And remember, we use the t-values, not the z-values. You only use the z-values for proportions. And here we have the p-value of 0.0003. Now, I'll show you how to use the calculator in a second to calculate some of these. But basically, a lot of the times you're given the information on a sheet that looks like this. Okay, so let's go ahead and construct a confidence interval for the slope. So whether you're doing it for the means, the proportions, or in this case for the slope, it's always the same formula. It's always the statistic plus or minus the critical value multiplied by the standard deviation of the statistic. Now, this is the formula that looks like, so our statistic in this case is going to be B, which is the slope, the sample slope. The T star value, that's going to be our T value from the tables. And then this SE subscript B, that's going to be our standard error of the slopes. So we call this a T interval for the slope. So whenever you're doing a confidence interval, make sure you use that name. Now, on the calculator, it says Lee Reg T interval, I actually don't think that appears on. Let me just check. Yeah, it actually doesn't appear on the TI-83 calculator. I think it does appear on the TI-84 calculator. So because it doesn't appear on the TI-83 calculator, what I'm going to do is I'm going to show you how to do it by hand. So here's the example that I already prepared. So first off, state what you're going to do. So we're going to construct a 95% confidence interval, albeit, if you were told to do a 99%, you would change that. So we're going to do a 95% confidence interval for the slope of the population regression line. So our degrees of freedom is always n minus 2 because we're looking at two variables here, and that's going to be 8. Here's our statistic for the slope, which is 4.43. Now the 2.306, you can get that from the t-tables. Again, use 95% confidence and use 8 degrees of freedom. And this number right here, that's the standard error of the slope, which we got from the Minitab table. So then you figure that out, and here's your confidence interval. So always make sure you explain it in context. So we are 95% confident that the slope of the population regression line is going to be between 2.726 and 6.134. Because we could do this test again, and we might get a different value. But we're 95% confident, or rather 95% of the time, the true value is going to lie between those two. All right, so let's go ahead and look at how we perform a significance test for the slope. So with a significance test, you need your hypotheses. So the hypotheses for this one are generally pretty straightforward. Because we're going to be looking for the slope, we use the beta here and here. So the top one is that the slope or the population slope is equal to 0. That's kind of like you would have like a horizontal, like a flat line where there would be no linear correlation. So the alternative one says that, hey, beta is not going to be equal to 0. That means there's going to be some positive or negative slope going on. So therefore some positive or negative correlation. So those are our two hypotheses. And remember, define the parameter. So here, beta is the slope of the regression line relating head size to height. And because no significance level was given, I'm going to use 0.05. So again, we know that the conditions have been met, and we can also make sure you do that for the confidence interval as well. And we're going to choose a significance level of 0.05 because none was given. So how do we interpret the data? Well, remember from the Minitab display, the p-value was 0.0003. That's less than 5%, so therefore we reject the null. So therefore, in context, there is sufficient evidence to suggest that a linear relationship exists between the head size and the height. Now you can also get these values from the calculator. So if you go down to linreg t-test, click on that. And by the way, I'm sorry, if you go to stats and then go to tests and then go down to your linreg t-test, there it is right there. Click on that. So then all our information was stored in L1 and L2. Frequency, leave that as 1. Now sometimes you'll be asked for less than 0, beta to be less than 0 or greater than 0. You would be looking at it to be greater than 0 if you were trying to test if there was a positive correlation. You would be using less than 0 if you were defining or trying to test if it was negative correlation. In this case, we're just trying to say, hey, is there a correlation? So we use the not equals to 0. Go down to calculate, and it's going to give you some data like this. Now, I really like this because it gives you a lot of information. So the first thing it gives you is the test statistic of 6.007. So if you're doing this using the tables and the charts, you can automatically see it graphically. It also gives you the p-value. Don't forget to check if there's like a little scientific notation there. So we've got a very small value of p, gives you your degrees of freedom, and it also gives you the y-intercept and the slope, as well as the standard deviation of the residuals and the correlation of determination, as also the correlation coefficient. So you got a lot of information there. So you could use that and then transfer that over to here to come up with your conclusion. So that's really basically all there is to it. Now you're going to need some practice. So therefore, you're going to be doing the assignment that's been set up on Google Classroom. The one thing I'll say though is on my AP, there are a lot of videos that go along with the theory behind this. I didn't decide to go through them because I felt it's more important that you understand the general gist and how to carry it out. However, if you're interested in why we do certain things or where certain values are coming from, I would strongly suggest you check out those videos. All right, so that's basically it for right now. Have a great evening or morning or day, whatever time it is. And if you need anything, don't hesitate to ask. All right, take care, everybody, and thank you.